Okay, good afternoon, everybody. We're going to go ahead and get started. And I want to introduce today's featured speaker. Uh, for those that are unfamiliar, I know there's some new folks and guests joining us. The Virginia Biosolids Council is a uh, group of wastewater uh, treatment facilities, as well as those contract and spread for the land application of biosolids. And our mission is really dedicated toward keeping the entire industry and process under a code of good practice to make sure we are following the science and research to make sure that we're using them responsibly. To that end, we've asked Dr. Linda Lee, who's a distinguished professor at Purdue University of both in the Department of Agronomy, as well as the Environmental and Ecological Engineering College of Engineering. She has degrees from the University of Florida in chemistry, environmental engineering, soil chemistry, and contaminant hydrology. And then she joined Purdue in 1993, where she has really pioneered and done the strong research program in environment, analytical tools, waste reuse, and contaminant management strategies, most recently with a background in research in PFAS, which is why we've asked her today. With that, I'll turn it over to Dr. Lee. Dr. Lee, thank you very much. She's going to give a overview of her work and research. And then as questions come up, or we're going to save some time for questions at the end, everybody is going to be muted throughout the presentation. Please drop them in the chat, and we'll give a reminder at the end. And we'll make sure we have enough time for your questions as we move. Take it away, Dr. Lee. Oh, you're on mute, Dr. Lee. Hold on.
Okay.
There we go.
Well, I guess it's good afternoon. It's lunch. In the US, it's easy to say good morning, but for some reason, good afternoon always comes out a little harder. Yeah, so I'm going to share a little bit on our research in the PFAS fate and transport and challenges in waste management. So I'll do a little bit on solids processing, some highlights of some recent work we finished, and then a few highlights from biosolid applied fields, a couple highlights on mitigation strategies that we're really testing at the lab scale now, but lab and greenhouse. And then a little bit on tile drains, because that's what impacts us in the Midwest, just to show you a little difference on how it might affect PFAS transport in terms of where it ends up. And then I'll just comment on some ongoing research. Don't really have a slide on that. And then Q&A. I had some other things I took out. I realized, okay, we just have lunch and learn. That's all we have time for. Okay. So I think we all know in this group, because you've been inundated with PFAS for a while, that it's a really large family of compounds with lots of different characteristics, lots of different classes within that family, all having lots of different chain lengths in the suite of compounds within each class, and then being unique to some functional group. And these are just the ones we know about. And there's a lot of new replacement PFAS that continue to show up on the market for different purposes. And then, as we all know, what's really, I don't think I need this nomenclature. So I just wanted to mention this because I know most people are familiar with what PFOS is and what PFOA is, where they come from. Some less familiar with these phosphonates that are becoming more and more prevalent in our biosolids. And in this case, they have that phosphorus group directly attached to perfluoroalkyl chains. Most of the other compounds tend to have this carbon hydrogen, 2 carbon saturated with hydrogen linkages, but again, you'll have a phosphorus group. So now our whole easy cheating way to name things gets a little harder, because now when we phosphorus containing PFAS, we mean both these PFAS that don't have any linkages and these, and where they mostly differ is that this linkage is easy to break microbial and otherwise. So interestingly, with all those thousands, luckily right now we're only trying to manage around regulations for a very small subset, and we're all familiar with these regulations that were just passed in April. Sometimes people have a little bit of lack of understanding on what that hazard index is, but other than PFOA and PFAS, it's basically taking whatever the target MCL is. So for example, 10 parts per trillion, that's your denominator. How much are you measuring? If you're measuring 5 parts per trillion, then that's 0.5 towards that 1.0 hazard index. And so you have to sum that up for the rest of these PFAS. So this is a little tricky when you're trying to meet guidelines, but I just wanted to highlight that. But still, these are some of the bigger drivers for us right now in terms of waste management and land application of biosolids. So I guess I should turn my camera a little bit better. So first I'm going to talk about just a few slides on some PFAS transformation in the solids as they come into the treatment plant that end up going into our biosolids. And just to remind us, I think I shared this in one other lunch and learn, but basically we have lots of different precursors. Those are things that we know can degrade, but just to other PFAS, eventually to the terminal PFAS that we refer to as perfluoroalkyl acids, or the PFAS. And they go through multiple steps and pathways, so you get lots of different intermediates during that path. During that process. And if they're telomere-based compounds where they have that little ethyl linkage group, then you can end up with whatever's the primary perfluorotail, but also several other carboxylic acids. Whereas the electrochemically derived, if they have an 8-carbon perfluorocarbon tail, then you're going to get C6 sulfonic acid. If it's an 8-carbon, like I'm showing here, you're going to get the 8-carbon, which in this case is PFAS. And these intermediates and terminal metabolites are just are more mobile than the precursors. And you'll see that that's why we call it multiplication, because you can measure a certain amount of PFAS coming in, and then all of a sudden you're measuring way more coming out or showing up in the biosolids. That's because there's so many things we can't actually quantify or even see in most analytical schemes. But once they get to these intermediates and definitely the PFAS, we can then see them. So we just finished some work with HRSD, Hampton Road Sanitation District, where we were looking at their solids coming into their anaerobic digester before they implemented a thermal hydrolysis process and afterwards. And so I wanted to just highlight a few things that we saw from this process. We analyzed what was coming into the digester, what was leaving the digester. In the case of once the thermal hydrolysis process was put in, we measured what was going into that, what was coming out, and then what was coming out of the anaerobic digester. And this is I feel like an easy way to show the data. So what we see here, we color-coded this pie chart based on PFAS groups. So PFCAs, or the carboxylic acids like PFOA, PFSAs, or the sulfonic acids like PFOS, and all the other chain lengths that have sulfonic acid groups on them. These fluorotelomere carboxylic acids, FTCA, and fluorotelomere unsaturated carboxylic acids, these are all intermediates on the way to the perfluorocarboxylic acids. Then you have some other precursors that sometimes can also be an intermediate, but your fluorotelomere sulfonates, they again have that, anytime you see fluorotelomere, they have that carbon, that ethyl linkage that's easy to break. And now we're saying phosphorus containing PFAS, which could be fluorotelomere ones or the phosphonates like I showed you, and some others. And then the sulfonic acetic acids, these are intermediates from electrochemically derived precursors that eventually lead to PFAS. So you can see for the anaerobic digestion, pre-anaerobic digestion, you can see how many precursors we had, P-containing precursors, plus you have all these intermediates that were already there, and some of these others. So everything except for these carboxylic acids and sulfonic acids are either intermediates or precursors. And you can see through the anaerobic digestion process, you get reduction in your phosphorus containing PFAS. We got some reduction in our intermediates, or some of our intermediates, because they're degrading and they're being generated at the same time. But you'll see we mostly gained in the perfluoroalkyl acids that are the ones we typically are monitoring, and all the commercial labs, are monitoring this suite of perfluoroalkyl acids. And then interestingly, so in anaerobic digestion, we had about 50% reduction in precursors and intermediates. So everything here, but the blue and orange. And then therefore you got this gain in the perfluoroalkyl acids. Now, once the thermal hydrolysis process kicked in, when that was started, what we saw was a large increase in we saw a pretty large increase in what appeared to be precursors and intermediates, or some increase, and a lot of increase in the carboxylic acids. And then when then the THP went into the anaerobic digestion, we did get conversion, but you can see that you didn't get as much conversion as you did in anaerobic digestion by itself. So it suggests that the thermal hydrolysis process does affect some of the degradation that happens typically in anaerobic digestion when you don't have thermal hydrolysis process before that. But obviously, and I'm kind of telling the choir, but thermal hydrolysis process was implemented to be able to handle a lot more waste at this particular plant. And that way you can have larger plants where you're able to implement in the future, in the next 3 years, if needed, implement treatment technologies. So this is a useful way to go. And so we just wanted to see what was happening with PFAS. And when you're looking at moles of fluorine that is associated with the organic compounds, they really increase a lot, but that's because our known precursors are degrading to lots of intermediates and terminal metabolites. And there's a whole lot of unknown precursors that we don't even know to look for. We don't have standards for, but once they're converted, we can see them. So that's why sometimes it'll seem like our municipal treatment plants are creating PFAS, and they're not actually creating them. Fundamentally, they're not creating them, but it seems that way. And then we also worked with another sanitation district who was doing thermophilic aerobic digestion and also doing storage nitrification and denitrification in series. And so what we saw in that, again, pre and post the anaerobic digestion part, but this aerobic digestion part, we saw lots of precursors converted, and actually many more than is converted in anaerobic digestion. So we had very little precursors left, and we had a lot of our long short chain perfluoroalkyl acids. And then we did see a reduction even in the fluorotellimer carboxylic acids. And then when we went into the storage nitrification, denitrification, the SNDR reactor, we did again see a shift in what types of compounds were there, and we saw a huge increase in the short chain perfluorocarboxylic acids. And really what's driving this in both of these processes, just like in the anaerobic process, is the microbial communities that are there, whether it's aerobic or anaerobic digestion. And we had some kind of different conditions that I don't have time to talk about that arise in the SNDNR. So these are all controlling your PFAS distribution and what you're going to see when you come out. So now I want to just talk about the fate and transport in the field. And so today I'm going to highlight a little bit of what's leaching through the soil, a little bit what can come into groundwater, and a little bit of what happens with runoff, all specific to just biosolids application. Okay. So most of us know once PFAS is land applied, it's going to undergo different fate processes that are very chemical specific and soil specific. So in terms of chemicals, we've already seen precursors can degrade, so we will have transformation happen. We also know that longer chain compounds stick to the soil more than the shorter chain compounds. We know soils especially agricultural soils that tend to have at least 1 to 2% organic carbon. We definitely see correlations with organic carbon. And then we also see see soil texture play a huge role, because something we don't have to deal with other organic compounds is this affinity for PFAS as surfactants to want to sit at the interface. So they will be sorbed to the solid phase, which seems to be dominated by organic carbon as far as the property that's leading to their association with soil. But then they also can accumulate it at the air-water interface. And this is becoming, more and more people are trying to model this fate, and we're going to know a lot more in the next couple of years. And biotransformation we already talked about. And then once it's land applied, you can potentially have plant uptake, especially as you have conversion to these perfluoroalkyl acids, with the shorter chains preferring to be taken up by plants. Maybe next year, if I come back and do a lunch and learn, I can share with what we're seeing in plants. I don't think I have any plant data today. And then it can also undergo leaching to groundwater, depending on where you are. It can undergo runoff, again, depending on your climate. And then we have, it says tail, thank you for my typo, but tile drainage that can happen in a lot of places in the country, especially in the Midwest. And all these things are very mitigated by, or very controlled by climate. Both how much rain you get, how intense it is, what kind of evapotranspiration do you have happening during the day, throughout the season. So it's really quite complicated, but this is the life of field studies. So first, an easy study just to highlight the transformation, because I don't think I shared this before. This was a WRF-funded project where we just did outside soil columns, where we mixed biosolids at 1 to 3% in a soil layer that was kind of representing the till layer. And then we had a very non-sorptive soil as the next layer, intentionally, so that we could see what is actually leaching from this till layer. And I think the only thing I really want to highlight here is you're looking at different water volumes as they've passed through the column over the six-month study. And what you're seeing, this dotted line kinds of represents what we would expect to see for carboxylic acids here and for sulfonic acids, based on what we knew was in the biosolids when we first mixed them in the soil. But during that time outside, you're getting that precursor transformation. And so what happens is you see more and more of these acids leaching out, way more than you would have predicted. And that should not be of a surprise to you now, because just like what happens in our treatment of solids in our treatment plants, the same type of processes can now happen in the environment. And one of the reasons I showed you the aerobic example is because in the environment, we mostly have aerobic, and you get much faster transformation. And you'll see that in our field studies as well. And you can see it also for the sulfonic acids, where they can increase. And it really varies with facility, mainly because it varies with what's coming into that facility and what their processing processes might look like. All right, so we're going to switch to field studies, and Kyle can raise his Zoom hand if he thinks I need to slow down. So we have a lot of field studies going on right now. And so I'll be able to share a little bit now with you, including some from Virginia. And then when I can come back in a couple of years, I can share on some of the more results. So here we have, this happened to be a site on the western part of the United States where there was a sanitation district that was applying biosolids every 5 years, but to different fields. And so we're thinking, wow, let's look at, what does PFAS look like in field A that was applied in 2019 versus 4 years ago, 3 years ago, 2 years ago, 1 year ago, and see if we see any kinds of trends in the PFAS that are just in the surface soil. Okay, this is just the upper foot. And we also measured the biosolids from that plant, and that measured the PFAS and the biosolids at the plant. So the PFAS and the biosolids at the plant had lots of precursors, fluorotellumer precursors, and electrochemically derived precursors. Remember, fluorotellumer ones will lead to carboxylic acids. The electrochemical ones will lead to the sulfonic acids. And there was really not, only about a third of the biosolids the third of the total PFAS present was actually the perfluoroalkyl acids that we talked about. But then look at what we saw in all the surface soils. We saw long chain carboxylic acids. We saw long chain sulfonic acids and a little tiny bit of short chain perfluorocarboxylic acids, and a little bit of the short chain perfluorosulfonic acids that are hard to even see. There was very little, we saw a little bit of the ECF precursors, but that's a little tricky because some of the precursors are actually intermediates from even larger precursors. But basically what you see, the distribution is consistently long chain sulfonic acid and carboxylic acids. If we look at a snapshot for 2018, 2019, 2020, you see that in this surface soil, the long chain compounds just continue to build up. Okay, so that's something important to remember. I didn't show you 21 and 22 because those fields actually had a little different application some years, and so that got a little confusing. So the big take home here is precursors, once they're land applied, convert very quickly. So this 2023 biosolid converted very quickly or it was a 2022 biosolid. They convert they're very similar over the last several years. They convert very quickly, and only the long chains are hanging up in that upper foot of soil. And then we had another study on the West Coast where we got to do a lot more work, where we actually looked at PFAS contamination, PFAS transport through the soil cores, and what was in groundwater at the site, and then also what was in one snapshot of biosolids. So this particular site has been receiving biosolids for 4 decades. And so obviously what's in PFAS has changed over time. But we had to look at, at least a snapshot of what was there. And so again, not surprising maybe, but, I showed you what was the other West Coast. What's happening here is this is the amount of P-containing and ECF precursors in the upper core, but mostly all long chain sulfonic acids and long chain carboxylic acids. And then you see a little that has transported to the next foot, but then pretty much everything else is almost non-existent on a relative scale. Interestingly, this particular site is not our typical apply at a fertilizer rate. It is applying at very heavy rates, because really I think I estimated about 70 times higher than what we would apply in a fertilizer setting. And also in a fertilizer setting, we're actually only applying typically only every other year or something like that. So you can see in this site, I wish we had soils from earlier, because this has built up a huge amount of carbon. So that's also contributing to this high retention in this surface soil. But you saw at the previous site, we still had a lot of retention in the surface soil, just for, I didn't show you the carbon, but for carbon in the 1 to 2% range. So you can see, again, we're getting everything built up in that surface soil, and it's mostly the long chain. And if we look at what was in the biosolids relative to what was in the core, again, the biosolids had a lot of precursors and intermediates, and then some long chain and short chain. But what we saw in the core was the short chains mobilizing, the long chain staying up in the upper surface soil. And this is now a proportional distribution, so you can't, it's not a concentration. And interestingly, what we saw in the groundwater was mostly just the short chain. But I thought what was really interesting is only PFOA, even in this dedicated land disposal site where you're applying 70 plus times more biosolids, municipal biosolids, than you would apply in an agricultural setting. Even in that setting, applying every year for 4 years, only PFOA exceeded the new EPA MCLs. I thought that was really interesting. Here's an example from the Midwest, a Midwest agricultural site that I threw in really quickly, that also has had 4 decades of biosolids, but now as a fertilizer. So at your normal rates, which are, like I said, at least 70 times less being applied to the soil. And so here I'm showing you just total PFAS concentration in 3 soil cores with depth. again, even in this very different climate, you still are seeing a lot of the PFAS staying in the upper 2 feet, although you do have mobilization. And then on the right, you're seeing the distribution that is showing up in these different cores. So you can see here, I'm sorry I didn't keep my color codes the same, but it's different students working on things. The long chains are in the greens here. So you see in those upper cores, they're mostly long chain. We did get some mobilization of the long chain, but we have more, basically more short chain. This particular site also is near a river, so it can flood from the river, and we know there are PFASs in the river. So it gets a little complicated at these deeper depths, but I really am just highlighting to you this correlation with carbon content and the fact that we are still getting greater retention in the upper 2 feet. So now here's a Virginia site. Here's a site in Virginia. This is Hampton Roads Sanitation District Progress Farm site. And you can see that this site was nice because it has, well, besides the fact that HRSD staff are amazing and wonderful, this site was great because it has 3 different soil types. So we would get to look at that. It also had an extra challenge, and every site has its own challenges, that it borders this lake that gets inputs from other sources, including potentially military sites that are within a few mile radius of this lake. And so what was kind of, serendipitous, I guess, because we didn't plan it that way, but because they wanted to go from Class B to Class A biosolids, we actually had a huge gap in biosolids application. So the last one that was applied was 2017, and until 2023. So we got to look at some interesting things at this site. And now if we took some soil cores, and this would, I will highlight that the soil cores that were taken prior to application of the new biosolid and after, they really don't look any different, okay? Because it takes a while for transport to occur. And the amount that you're adding from one application at fertilizer rate doesn't really compare to several years of applications of biosolids. So there was really no statistical difference even in the upper foot. But we can look at what happens with different soil tech types. So here is a silt loam, and you can again see this trajectory we've been seeing with the long chains really staying up in the top 2 feet, but we do get some mobilization. This is with depth, kind of in 30 centimeter increments. Here is a loam soil that's in another part of the property. And here your texture is not going to be as fine, and you are actually getting some, a little more mobility with your long chains than you saw in the Acrodel silt loam. And then our sandy soil, we're seeing even a lot more transport. Now this gets tricky, but what we're seeing here is what really appears to, I don't have all the soil carbon data, it's been measured, and the texture data, and the student Linda Peters, she actually did measure texture on every single sample of every core. So it'll be interesting because what we think we're really seeing here is a signature of what's happening at that air-water interface, because more finer texture soils can have a lot more air-water interface showing up. And so this will be really interesting as we explore all the mechanisms that are happening at this site. And that's something that we'll be hopefully able to share next year. It'll be getting written up for publication. And I want to show you one other Midwest site where we were actually using lysimeters at 2 feet and 4 feet to see what was happening. This was another Midwest site where, oh, I think I already showed you this. Yes, I did. So we get to go by it. Okay. Sorry, I put in better slides and forgot to delete theirs. So we've looked at leaching through the soil profile, and there's really some very, very consistent trends. Long chains accumulate near the upper 2 feet, but you can get mobilization depending on soil texture, climate, and even carbon content. Now let's look at the other pathway that PFAS can leave our farms, and that would be through runoff. And so we can have runoff, with increasingly more intense rain events. I see it here. And then that can go into a ditch network or stream, which then can eventually go to a wetland or a pond. And so we're doing a lot of work in this space. And I will show you some different, just a few snapshots of what we're seeing in runoff. So here's one example of runoff on our East Coast site. So this can be a little complicated, but on the left, what you're just seeing is that, flow rate over time. And so you can imagine that as you have intense rain events, you're getting a lot of flow in runoff flow. And then, so we'll call it flow rate, so runoff flow. And then you can see total PFAS that are being measured in samples during this runoff event. And you can see that when you're looking at concentrations, the concentrations are higher at low flow because you're not diluting. But once you've accounted for the amount of flow, just like what's happening in our treatment plants, we know that industry and landfill leachate can have really high PFAS concentrations coming into our plant, but the actual volume coming into the plant is small compared to domestic sewage. And so what we're finding at a lot of plants is that domestic sewage is the big PFAS load. Even though the concentrations are low, the actual amount of PFAS coming into the plant is dominated by sewage, domestic sewage, which, creates a huge problem and sends the message that, hey, we need PFAS out of our products. But once you account, now you see that that during heavy flow, you will see more of the PFAS coming out. Now this has been normalized to flow. So you'll see the PFAS loads correlate with that intense runoff event. And then if we just look at what is in this runoff, and it's in nanograms per liter, but remember it contains solids too. So there's not, we have to work on the best way to show it, maybe mass loads, but you see normally the shorter chains that we see a lot of in terms of leaching to groundwater, that's not what we see in runoff, which you shouldn't be surprised. We see long chain because the long chains are what's sitting in the upper 2 feet of profile. And even though PFAS is becoming lower and lower in our biosolids because of phase outs, it is still the one that hangs out the most. It does have the highest affinity out of these acids to sit at the air-water interface. And it's just going to be a challenge for us to have to deal with for a long time. And so unrelated to this site, okay, so it's really important to know that. Unrelated to this site, I'm going to show you, if we look at PFAS from in fish from different water bodies, where we know things that are considered reference sites, this is just literature pulled together, versus sites that could be impacted by biosolids. They say biosolids affected, but you have to dig in deeper to know for sure. And what EPA did in background, and this was out of Indiana's database for Indiana and some other things. You can see that, it seems that bluegill and largemouth bass do tend to have a higher bioaccumulation of these materials. And you can see that in the biosolids affected sites, they seem to have, on average, more in those sites. And you won't see very much in the water and sometimes even in the sediment. So that can be misleading to just measure what's in the water and the sediment. So we've been looking at some ponds in Indiana. And here's an example of one where, let me just put my talking points, where you can see this is a biosolid affected pond because it's a pond sitting in an agricultural field that has received biosolids. And then a reference site that is supposed to be, it does not have any biosolids. Okay, so we'll talk about, why we're seeing what we're seeing. First thing is you're definitely seeing more, and it's primarily PFAS. I lost my color code here. This red is all PFOS. Everything else is some other materials, other PFAS. And you see that that's what's dominating. And in the water and sediment, you don't see a lot, but your bioaccumulation factor into these fish, turtle, bluegill is substantial so that you see this. And we consistently see it more in the largemouth bass and bluegill. And if you look at our reference site, you see that we still see a lot of PFAS, most of it PFOS, this red. And that's because this is actually being impacted by a large animal feed operation. And animal feed can have PFOS in it, can have PFAS in it. And some of the bedding and some other things that happen at these sites. So, no matter how hard we try, we cannot get away from PFAS getting into our ponds. And it's not just biosolids, but I thought that this connected well to understanding possibly management strategies when we're applying biosolids. If they get subsurface injected 8 to 10 inches below the surface, maybe that reduces their runoff potential versus disking at 2 to 3 to 4 inches at the surface, and definitely versus broadcasting. So these are things we can think about, which affects everything upchain too, about what's the best way to land apply. And then, of course, PFAS gets into our atmosphere. And I wanted to show this because here's an example of where we measured rainwater 3 months in a row, and consistently we saw PFAS in the rainwater. Not so surprising, but what was surprising is that PFOS, these are the darker parts of the bar, they exceeded EPA's standards for drinking water in 2 of 3 of these samples. So where is this coming from? Is it coming from aerosols from the treatment plants? Is it coming from aerosols at military bases? And is it coming from, prior or existing, activities? I know I have been to a fire training exercise, and at the time, it's different now. At the time, it just looks like soap foam going everywhere. And I watched them do their fire foaming testing, and watching foam fly everywhere into the air and into the forest and into the trees. So, this is why we really have to be mindful of even rainwater when we're doing things at sites. And when you think about reference sites, same thing. It's going to be impacted by whatever atmospheric deposition is happening. And so I have a lot more field studies, but I feel like I got the message across. What I want to just highlight briefly, really just with I think only one slide that I actually made, is looking at potential mitigation strategies. So I wasn't sure if I shared before, so I didn't include it, is mitigation strategies from mixing biosolids with other types of non-PFAS containing materials, mulches, ground, sawdust, whatever it is. And we did see, it's a study that just got published. So I at least should have put that up there, but I can send it to Kyle to post. Just got published in Journal of Environmental Quality, where we do see some positive impacts of mixing PFAS containing biosolids with other organic amendments to reduce PFAS leaching. And it mostly impacted the longer chain, leaching of the longer chains. And that was a lysimeter study that we didn't design, but we were able to jump on and do PFAS work in that. The second thing we're working on in both the lab and greenhouse, strategizing for field studies, one field study has already been started in Maine, is looking at adding sorbents that can, mixing them with the biosolids in this lab study. In our field study, we're mixing them in field soils that have already been contaminated with biosolids of different origins. And what we're seeing here, what you're seeing here is these were simulated rainfall events that were imposed on columns that had biosolids mixed in with the soil at a couple weight percent, with and without the addition of sorbents. The 2 sorbents we used was a pyrolyzed biosolids, which we'll refer to as biochar here, and some aluminum chlorohydrate water treatment residuals from the Swift plant there in Virginia. And even though, for a field scale demonstration, these ACH water treatment residuals would be very hard to get the amount you would need, we still wanted to see how effective they were, because no one had done work on those, only on other types of aluminum based like alum. And what you can see here, if we look, it's easiest to see in the cumulative amount leached, but you can see this is what leached from the biosolids compared to what was leached with the biosolids mixed with a few 8% of ACH residuals, treatment residuals, and the biochar. And you can see overall your cumulative leached was similar between treatments, although they did have some variations, but I'm not going to bore you with all the details on that. But we do have a couple grants where we will be exploring other types of sorbent additions to potentially reduce PFAS mobility, either from soils that are already highly contaminated or actually as a being able to amend with biosolids. And I just want to mention some other potential mitigation strategies we're looking at. We're doing some greenhouse studies with some different plants and grasses and soybeans, both to look at what's being taken up, but also to see if plant species can vary and other kinds of management strategies can change the amount of PFAS that might get taken up in the plant that people might want to use for feed or whatever food products. We're also looking at working with Merrill Brothers here in Indiana to we're now on our third treatment experiment, looking at a combination of foam fractionation and hydrocavitation for removing PFAS from biosolid slurries, so that we can then apply the biosolid and not lose its value. They're also doing supercritical water oxidation there. But the benefit to this foam fractionation and hydrocavitation is that you're not losing a lot of the other values that we value biosolids for, their carbon and the nutrients. You're not necessarily losing them in that process. So I hope by next year, as I continue to work with them, that I'll have data to share with you. And lastly, I just wanted to show you again another mode of PFAS leaving our fields and getting to places where we might not want them, for a site in Indiana. So in Indiana, we focus just in the county I live in, and we have very heavy agriculture, but also almost every agricultural field is tile drained. And I think most of you probably know what tile drainage is, but basically a meter below the soil surface, you are seeing perforated tubing that's taking the water off site. So it's never percolating to groundwater. It's only getting discharged into ditches that go into the stream. So it's probably not surprising to find out that we had very low PFAS in 100 groundwater, rural well water samples in this area that we tested. Very little. We did get a whole suite of them for frequency of detection. We see the carboxylic acids the most, but look at the concentrations. None of them are of concern. None of them are levels that EPA would say, hey, we need to do something about this water. So this is good, but then I said, this is probably due to tile drain discharge. And still, this is a hypothesis, but the first thing we did was, well, let's measure in the streams all in the county. And interestingly, and not surprising, we saw more detection and we saw much higher concentrations of total PFAS. But even with that, our PFAS levels were not so bad. But you can see that instead of being down to, single digits, we're now up to double digits for total PFAS that's showing up in the rivers. So rivers are tricky, streams are tricky because they get upstream sources, but it does kind of infer some of our hypothesis might be correct about tile drainage. And so that is some other studies that we have underway, which are looking at having a hard time getting a tile drain. I have 2 tile drain sites that I'm supposed to be doing, and still having a hard time getting the right site. It has to have biosolids applied, have to be able to get access to where the drain comes out, which is not usually on the farmer's property. And you want to know that you have clear understanding of what fields are being drained by the tiles. So it's been interesting. And I already talked about that. But one thing I wanted to mention, because most of us we care about the municipal biosolids. And even in Maine, we've had our issues in our conversations about some of the sites in Maine and accusing it of being municipal biosolids, but they were not typical municipal biosolids. Because what I'm showing you right here is a signature that I see even in Indiana for any sites that have gotten paper mill sludge. They do not have the same signature at all as municipal biosolids. They have very high PFAS, very high PFAS precursor, this ethyl, and it can be methyl too, FOSAA. and very little of anything else. So this might represent, and this might represent a little bit of municipal biosolids that were applied to these fields, because that was more years than not. It was municipal, but this tells me this is dominated by paper mill input, and whether it was paper mill coming into the municipal treatment plant, exactly like what I have in Indiana. This signature is really important, and it tells a big story, because we really want to differentiate this very few percent of solids that are actually the biggest problem. And then this is Q&A time, but I like to end with when chemicals go to the dark side, because we all used to love PFAS for what they did for us. Just unfortunately now we don't love what we're having to deal with. So Kyle, do you want me to stop share for Q&A?
Actually, I think we want to leave you up because there's a few questions that have popped into the Q&A chat that deal with some of the slides. So if you want to reference back to them, you can. So
I know
for
that
example,
was a lot fast. Sorry.
It's all right. We ask you to do a lot of time, and we will definitely have you back, Dr. Lee. The 40-year historical dedicated land disposal site that you referenced from before. The question came in is, why was there so much biosolids being applied at the site? Is it a reclamation site? Or it seemed to the questionnaire, I think, that there was a lot of, that was a lot for land application.
It is a lot for land application.
Right there.
It is a lot for land application. It was exactly what it says, dedicated land disposal. So that sanitation district was putting all their biosolids from that plant onto this, was it like 9 acre site? And I told them, you don't want to do that. And so that's one of the new sites is they now have a almost like 275 acre site that we are going to be monitoring PFAS fate from the beginning. So their first application, it's dry farmed. We're looking at what's in crops. We've already started. We're also looking at other unregulated organic compounds, but I just focused on PFAS today. So next year I can talk about those. And so, but interestingly, even though I said, you don't want to do this anymore. So they moved to this larger land application scenario. And that was before I have all the data. So what I thought was interesting, I really was surprised that, and of course, PFOA is a problem, and this is not drinking water, but in the well that's directly impacted by this heavy land application area, only PFOA exceeded the MCLs of EPA for drinking water. I was really surprised, but it's because one of the things that people don't consider is all the carbon that was getting added to the soil. It doesn't change the fact that we still, they had a big flood last year. So who knows how much runoff issues you had from the site with all that PFAS, pretty high concentrations, right, sitting in the topsoil. So we don't want to do it this way. But even to me, even doing it this way, we didn't end up with a ton in the groundwater. So it was surprising. So.
So another question was, what kind of biosolids were applied in the field studies that you referenced prior to? I know in the Virginia one you had class B started with, and then going to class A. Were the other field studies the same that you referenced from the Western USA? AD, lime, were there other additives applied to it as well?
So most of them were AD were anaerobic digestion that have been applied. And I think most of the ones I showed you today, if I'm not mistaken, are class B. And, class A versus class B really doesn't impact PFAS very much. Maybe a little bit in the distribution if when you lime, you get some conversion. But it's really, right, looking at pathogens and things like that. So it's not doing a huge amount to with PFAS. So even though it was class B, it's not going to change the trends that you see for PFAS, really.
So we're back here on the slide called impact of pre-digestion, kind of one of the first slides you showed. Is that a reduction of PFAS compounds, or is it more conversion then reduction in quantities remain the same.
This was reduction in precursors and intermediates. So these compounds were reduced by half. These compounds doubled, the acids. So you definitely increased your total moles of, your moles of PFAS molecules, but the precursors and intermediates a lot of those go away. Not everything, but about half. And you get a lot of terminal carboxylic acids and sulfonic acids generated. So I'm glad you asked that. I shared this with somebody right before this on another meeting because we were trying to, it was a WRF pre-proposal that got accepted for full and trying to think about what plants we might want to invite to do it. And I showed him this and he also got confused. So I'm going to have to highlight precursors and intermediates in this slide, especially when I go so fast. So sorry about that.
Oh, no worries. One of the things that as you were scrolling through on your mitigation techniques, slide 27, it didn't show any of the actual techniques.
That's because I ran out of time because of my meeting before this.
It's fine. We will.
My bad. Just like that. Yeah, but I did mention. So future work we have a greenhouse study where we are looking at different additions. A pyrrolized wood it's a wood ash, pyrrolized wood, at different application rates. All the plants are growing, all the grasses, we went up to I think 6 or 8%, and they're all happy campers. So we're going to be looking at PFAS in different cuttings first before we take it down. So because we know the evapotranspiration and how young the plant is seems to, at least in the field, affect PFAS uptake. So looking at that, because again, if there's things we can do in the field, even in the growing plant side, to minimize PFAS uptake, because we can't just, not have all of our agricultural land banned because we have PFAS present, for more reasons than just biosolids. And then we are also doing soybeans, 8 different varieties of soybeans, and in one case looking at adding again the wood ash to see if it changed what gets put in the bean. For people haven't reported of what's in soybean beans around here. There's been a couple PFAS plant studies, but they didn't look at the bean. I don't know why, but to me, you look at the part that's going to go into the food chain.
We did do a soybean, where we have a soybean test plot over on the Eastern AREC that VBC is sponsoring. So we're hoping to have some of that data as we move through. Dr. Oakes is looking at that for us. I know Dr. Z is looking at it for pasture land in the western half, which I will put a plug in right here for our next lunch and learn in July. We'll have Dr. Z from Virginia Tech on to discuss her research and what she's seeing.
I was going to say, I did grab soybeans from biosolid applied fields in our county. They're totally fine. And they've been getting biosolids for several years too, but at agricultural rates, subsurface injection. Yep. And I didn't see, PFAS was municipal to negligible in those beans. So that's encouraging.
Are you or others planning to work with land application of lime stabilized biosolids? And do you expect different results from these biosolids when it comes to lime stabilized?
Yeah, I don't know. So it's possible we could include them in some of the new field studies that haven't been started yet. I'm in a year of planning for one of the USDA grants. If I had to guess what would happen, once you mix biosolids with soil, you might have some impact of the biosolids on microbial communities. You might have some, soils have such a buffer capacity. So I don't know how much the pH of the biosolids or the microbial communities of the biosolids are really going to affect long-term what's happening in the soil. So if I had to guess, that they're not going to impact fate and transport much. What they might impact in the processing is a little bit shift in PFAS distribution, because you might actually get some additional conversion through the lime stabilization.
And lastly, and this kind of the last Q&A is where I was going to wrap up. We do have some policymakers on. We do have some and some interested stakeholder groups on that. For the layperson, obviously we see a lot of data coming at us. We see a lot in the media coming at us, and obviously we just can't stop applying biosolids. As I said before, it's a byproduct that's going to keep coming through our wastewater processes. What are kind of three takeaways you see or through your research that would benefit the industry, or not only three takeaways for that, but what you see going forward and what we need more research on before making a decision?
Yeah, so we definitely need to be regulating PFAS production and use. That's a given that I didn't show you any data for this, but given the PFAS loads that are coming in from domestic sewage that we cannot control at the household. Secondly, we need to, I think the research in the treatment area is really important, especially given that in about, right now, all the municipal plants, right, are having to monitor and report, right? And then after 3 years, if they have issues, and I know it's, focusing on everything focused on drinking water still comes back to affect everything in the plant. So we are going to need treatment technologies, both for drinking water, but also for biosolids. And so I really think in the next 3 years, we are going to see scalable treatment technologies for biosolids. One thing I didn't say, and I saw it. So that pyrolyzed biosolid that we used, I've showed before where it, once you pyrolyzed it, almost nothing leaches out of that biochar. But the PFAS are in the biochar. And the first time I ever noticed, which was just this week, all the precursors, ECF precursors, after the biosolid was pyrolyzed, they were gone, and PFAS increased at about the same magnitude as the precursors disappeared. So that tells me, and this was low temperature pyrolysis, 350 degrees. So that tells me at low temperature, I was surprised that you got that kind of conversion. So obviously that's one other type of treatment, but that's what made me think of it. But I think treatment technologies for biosolids so that we can still safely land apply is really important, because it's not sustainable to think we can landfill them all or even pyrolyze them all. It's just not sustainable. And then better understanding how much PFAS on what soils for what plants is a problem, right? So we have what's going into the food chain and what's going into our water supply. So it's kind of both ways.
Excellent. Well, with that, we're going to wrap it up. Thank you so much to Dr. Lee for taking the time. And any other follow-up, we have been recording, so we will post just attendees that registered so that you can go back and see it. Please, any other comments, questions, direct to myself as VBC secretary. Thank you again, Dr. Lee. Look for invitations to our upcoming Lunch and Learns with Dr. Z. We also know that
That'd be great.
Dr. Ian Pepper's research is ongoing, of which our Eastern Virginia AREC submitted data to. So there will be a Virginia component. His report is scheduled to come out later this summer, and we are hoping that once that data and report is public, we're going to invite Dr. Pepper on to come on for a Lunch and Learn as well. So an awful lot of research going in the biosolids space. Thank you very much, Dr. Lee. Thank you all for joining, and enjoy the rest of your day.
Thank you.
Thank you so much.